Hey everyone! Hihu here from LeetCode. Today we're solving LeetCode 643. Maximum Average Subarray I. This is an easy difficulty problem. And it comes under Arrays and Sliding Window in the LeetCode 75 study plan. At first glance, this problem looks straightforward. We're just asked to find the maximum average. But if we solve it the obvious way, we'll end up doing a lot of repeated work. The interesting part isn't calculating the average. The real challenge is calculating it efficiently. So let's first understand exactly what the problem is asking. We're given an integer array called nums. We're also given an integer k. Our task is to find a contiguous subarray whose length is exactly k. Among all such subarrays, we need to find the one with the maximum average. Finally, we return that maximum average. Notice two important things. First, the subarray must be contiguous. We cannot skip elements. Second, its size is fixed. Every subarray we consider must contain exactly k elements. Now let's understand this with an example. Suppose the array is 1, 12, -5, -6, 53, and k is 4. Since k is 4, every subarray we consider must contain exactly 4 elements. Let's look at the first window. It contains 1, 12, -5, -6. The sum is 2. So the average is 0.5. Now move one position to the right. The next window is 12, -5, -6, 50. The sum becomes 51. So the average is 12.75. Move one more step. Now the window is -5, -6, 53. Its sum is 42. The average becomes 10.5. Now compare all three averages. 0.5, 12.75, 10.5. The largest one is 12.75. So that's the answer. Notice something interesting. As we move from one window to the next, most of the elements stay exactly the same. Keep that observation in mind. It will become very important later. But before we get there, let's think about the most straightforward solution. The simplest idea is easy. Generate every possible window of size k. For each window, calculate its sum. Then compute its average. Keep track of the largest average we've seen. Once every window has been processed, the maximum average we found must be the answer. This solution is simple. It's easy to understand. So let's see how we'd write it. Let's convert that idea into code. First, we create a variable called maximum average. Initially, we can set it to a very small value. Now we generate every possible window of size k. The first window starts at index 0. The last possible window starts at array length -k. For every starting position, we calculate the sum of the next k elements. Once we have the sum, we calculate the average. That's simply sum divided by k. Now we compare this average with our current maximum. If it's larger, we update our answer. After checking every possible window, we simply return maximum average. The algorithm is easy to understand. But let's verify it with a dry run. Let's use the same example. The array is 1, 12, -5, -6, 53, and k is 4. We start with the first window. It contains 1, 12, -5, -6. To calculate its sum, we add every element. 1 plus 12 minus 5 minus 6. The sum becomes 2. The average is 0.5. So our current maximum average is 0.5. Now we move to the next window. Again, we start from scratch. We add 12 minus 5 minus 6 plus 50. The sum becomes 51. The average is 12.75. That's larger than our previous answer. So we update maximum average. Now we move to the last window. Once again, we calculate the entire sum from scratch. -5 minus 6 plus 50 plus 3. The sum is 42. The average becomes 10.5. That's smaller than 12.75. So our answer doesn't change. After checking every possible window, the maximum average remains 12.75. The solution works perfectly. But while doing this, Did something feel repetitive? Every time we moved the window, we added almost the same numbers all over again. That feels unnecessary. Maybe we can reuse some of the work we've already done. Let's analyze the complexity. Suppose the array contains n elements. There are roughly n possible windows. And for every window, we calculate the sum of k elements. So the total time complexity becomes O of n multiplied by k. Now let's talk about space. Did we create another array? No. We only used a few variables to store the sum and the maximum average. So the space complexity is O of 1. The space usage is already optimal. But the time complexity can still be improved. Because every new window looks very similar to the previous one. Can we somehow reuse the previous window's sum, instead of calculating everything again? Let's take a closer look at two consecutive windows. The first window is 1 12 -5 -6. The next window is 12 -5 -650. Now compare them carefully. Did every element change? No. 3 of the 4 elements are exactly the same. Only one element left the window. And only one new element entered. That's a huge observation. But what did we do in the brute force solution? We added all 4 numbers again. Even though 3 of them were already part of the previous sum. That's unnecessary work. Instead, why don't we reuse the previous sum? Think about it. The previous window had a sum of 2. To get the next window, what actually changed? The number 1 left the window. The number 50 entered the window. Everything else stayed exactly the same. So instead of adding all 4 numbers again, we can simply update the sum. Take the previous sum. Subtract the number that's leaving. Add the number that's entering. And now we have the new window's sum. No repeated calculations. No unnecessary additions. That's the key observation. Whenever we're working with consecutive windows of a fixed size, most of the data stays the same. Instead of recomputing everything, we reuse the previous result and update only what changed. This technique is called sliding window. Now let's see how we use this idea in the optimal solution. We'll first calculate the sum of the very first window. That gives us our starting point. Now we begin sliding the window one position at a time. Whenever the window moves, one element leaves and one new element enters. So we update the sum by subtracting the outgoing element and adding the incoming element. After every update, we calculate the new average. If it's larger than our current maximum, we update our answer. Then we slide the window again. We repeat this process until we've reached the end of the array. Now let's translate that into code. Let's convert this idea into code. First, we calculate the sum of the first k elements. This becomes our initial window. We also initialize maximum sum with this value. Now we start sliding the window. The next window begins one position to the right. To update the sum, we subtract the element that's leaving the window. Then we add the element that's entering the window. Now we compare the updated sum with our current maximum. If it's larger, we update maximum sum. We repeat this process until we've processed every window. Finally, we return maximum sum divided by k. That's the complete optimal solution. Notice something interesting. We never recalculate the entire window. We simply update the previous sum. Let's use the same example. The array is 1 12 -5 -653, and k is 4. First, we calculate the sum of the initial window. 1 plus 12 minus 5 minus 6. The sum is 2. So our current maximum sum is 2. Now we slide the window one position to the right. Which element leaves? 1. Which element enters? 50. Instead of calculating the whole sum again, we simply update it. Current sum minus 1 plus 50. The new sum becomes 51. That's larger than our previous maximum. So we update maximum sum. Now slide the window again. Which element leaves? 12. Which element enters? 3. Again we update the previous sum. Current sum minus 12 plus 3. The new sum becomes 42. That's smaller than 51. So our maximum doesn't change. We've reached the last window. The maximum sum is 51. Now divide it by k, which is 4. The answer becomes 12.75. Exactly the expected output. Notice how we never recalculated an entire window. Every new sum came directly from the previous one. Let's analyze the complexity. First, we calculate the sum of the initial window. That takes O of k time. After that, every new window is updated in constant time. We process the remaining elements only once. Overall, the time complexity becomes O of n. Now let's talk about space. We only use a few variables to store the current sum and the maximum sum. No additional arrays. No extra data structures. So the space complexity is O of 1. Let's quickly recap. We started with the brute force solution. For every window, we calculated the entire sum again. The solution worked. But it repeated almost the same calculations again and again. Then we noticed something important. Consecutive windows overlap. Only one element leaves. And only one new element enters. So instead of recomputing the whole window, we updated the previous sum. That's the interview pattern to remember. Whenever you're working with consecutive subarrays of a fixed size, ask yourself this question. Can I reuse the previous window instead of calculating everything again? If the answer is yes, you're probably looking at a sliding window problem. And that's how we solve LeetCode 643. Maximum Average Subarray I. If you found this explanation helpful, make sure to like the video and subscribe to LeetCode.